Welcome back to our last session, and we will start with Petri Lievonen, who has been working quite intensively over the past 2 years with the dynamic universe. There's a very nice page of simulations available in the dynamic universe website, and today Petri will tell us about mathematics in DU and SRGR.
Okay, thank you very much. Yes, during the last 2 years, part-time, I have been helping Tuomo and studying his work, discussing a lot. So I feel a little bit of responsibility, even a commitment to discuss and present these things and my findings, especially because there are so much that kind of like implicit knowledge or hidden knowledge which only comes through when you discuss with Tuomo directly. But also, I must confess that this is a really like difficult topics, because of course these are quite deep when you go deep to the details, and it's usually easier to talk about concepts where you have good textbooks and we have common concepts, common references, common experiments, and common interpretations of the experiments. So, for example, general relativity, some like black hole studies or something, but now here we have to sort of connect between different domains, and let's see how it goes. So, as this is this kind of a workshop situation, I have prepared quite relaxed talk. So I have few slides that I have just now inserted there due to the questions that we got yesterday. So let's see if I can go through them too. So last spring I started with this, like a short course in general relativity book, and discussed it, especially like these like two main, because this is like the first image in that book already, and two main like categories of phenomena, but also problematized or like brought into discussion in a sense that what is a matter at rest, what it really is, how should we conceptualize it, and also light like what is those are like extreme cases that could help in discussing some situations. I also I wondered also before that if Suntola's ideas could be conceptualized as standards, SE standards, so operationalization of standards such as meter, second, kilogram, ampere, other SE units, and how that might give new ideas to physics generally also. So this time I thought that maybe I'll take one slide from Tuomo's presentation, and then somehow wrap this story or this flow around this single slide. So this is quite a cryptic slide for many, but one can perhaps see that there's like cosmological considerations, there are like astronomical considerations in terms of like gravity and black hole physics, and then there are like local considerations which like deal with energy momentum relations and stuff. So these are like the problem with DU and these Suntola's ideas is that because it's for example, variable speed of light theory, and variable speed of light theories are really like notorious to get them to consistent. They affect everything. They are in literature, of course, they are these kind of like ideas and theories, but to really get it consistent, it would affect so many phenomena that it's then difficult to extract one single like domain out of that. It could be easy for me to discuss the three-sphere geometry. So three-sphere unique, nice geometry because it's parallelizable. So it admits three linearly independent, non-vanishing vector fields. So there's no Hairy-Bolt theorem doesn't have any singularities. So you can always draw these kind of like really simple great circles because you can simply slice the three-sphere however you wish. But it would perhaps be like too easy in a sense, because these and maybe it's important to emphasize that these results that Tuomo mentioned and presented yesterday, they actually don't need any of, or at least most of these mechanisms or these domains at all. They are mostly just like three-sphere geometric results. So these kind of the angular sizes, you can derive it by simply looking at three-sphere geometry. Also that lensing effect, theta divided by sin theta, where theta is the central angle, it's like also a geometric. And here in the supernova results, then you have to take into account or somehow discuss the energy propagation through space. And there you need to make some assumptions. But still you don't necessarily need the energy balance equation or something like, because it's like pure geometry, and there are these kind of relations where the light propagation in the three-sphere and the hyper-radius expansion are linked in such a fashion that actually the variable speed of light even doesn't affect these graphs too much. So this is a nice thing that there are these kind of predictions, and when new data will become available, then we might actually see some interesting discussions in the future. And especially this is quite wonderful because this is so weird prediction, because it's a prediction that actually that there would be like antipodal point to this positive curvature universe, unique antipodal point to each point where we are, for example, now. And if there would be something at the antipodal point, then you could see it from every direction, because every great circle converges to that same antipodal point. So in that sense, the antipodal point would be magnified across the whole sky. And then, because the energy is, of course, conserved in that sense that it doesn't get any more brighter, then DU or Suntola predicts that this redshifts here will be like a new dark era, in a sense that we don't get too much measurements from there because they are so dim, because they will be all around the sky. And also if we somehow manage with modern future instruments to see these really high redshift objects, then the light could be traveling around the universe from both sides. So actually you could have you could predict, as Thomas here has done, that exactly at the opposite point you should see the same object from other side and actually predict its redshift also. But this is, of course, cosmic microwave background, the baryonic acoustic oscillations, there's no work on that. So this is, but still, this is how it's. I think it's interesting. Okay, so but then I thought that maybe because this one is important for Tuomo, this kind of like circular representation or almost Euclidean representation of energy momentum relations. You can see it is in his mass concept, and this how instead of thinking that you bring energy to system to accelerate it, you bring mass, this kind of abstract mass. So I could discuss that a little bit. then if we have time, I could discuss the Tuomo's ideas how like Schwarzschild solution in general relativity could be, because there's this Flam paraboloid solution, and with this Tuomo's formulas, you get a little bit different Flam paraboloid. So it gives different kind of solutions around black holes, and it might be really like a nice thing to discuss. And also then the variable standards, which we referred yesterday. So there are a lot of things to discuss. So because I'm somewhat familiar with Clifford algebras and geometric algebras, I also feel compelled, but responsible to somehow always bring them into picture in some way. So this is really amazing talk by Anthony Leisenby from just a year back, and I collected some of the like just as a gestalt, as we don't need to go all through it, but as a gestalt of what space-time algebra and these kind of like four-dimensional algebras or four-dimensional spaces in what they could bring into this picture. And DU has not yet been formulated with geometric algebra or space-time algebra, but I can sense that there could be really wonderful avenues for clarification there, because instead of going straight through to differential geometry and these field equations, these algebraic approaches have that kind of like a quality of being able to make diagrams. But I will shortly go this. So in space-time algebra, you think about the laboratory frame, and then you, because this is a CL, let's see if I have here, yes. This is a Clifford algebra 1, 3, so there's one basis vector that squares to 1 and 3 basis vectors that square to minus 1. So when you multiply those together and take all the combinations, you get the scalars, which are like point-like quantities. Then you get 4 vectors, which is a mixed signature. 1 like time-like and 3 space-like. But then interestingly, you get 6 bivectors, which are like 3 and 3, and sometimes they are marked like they are time-like bivectors and space-like, or Lorentzian and space-like bivectors. But interestingly also, sometimes they are called magnetic and electric bivectors. And that's, I think, quite interesting, like division between these different elements. Then there are 4 trivectors and the pseudoscalar of the algebra, which is like a 4-dimensional oriented volume element. And then you can get down to this Pauli algebra by multiplying with this time-like gamma 0. And the interesting thing is that the 3-dimensional volume element is the same element as the 4-dimensional volume element, algebraically, in this algebra. So there's the volume element, in a sense, it's somehow really like common to 4 and 3-dimensional spaces. For example, you can see then, because it squares to minus 1 and it commutes with all the basis elements in 3-dimensional setting, then it works like a complex imaginary number. So in this imaginary element, so for example, Compton frequency can be in some senses described as, you know, space like turning inside out, this kind of pseudoscalar oscillation. And with these algebras, you can follow them through. And then there are these 4-dimensional, all these elements are here. So you can take the even algebra, only the even elements, which which consist of these, and they make the three-dimensional Pauli algebra. And this is why I wanted to show this, because then this is quite interesting, for example, here in this talk, that we don't need to go into details how the octonion products and this kind of higher level products here work. But you can see that the spinor is the J dotted with this time-like gamma naught, and the J is the like rotor or this kind of sandwich product between this sandwich product with this time-like gamma zero. So that is just intuitively, it has that kind of a feel that, for example, that Tuomo also considers, that you have this time-like, even though it's not exactly the same, but you have that time-like extra dimension here, the fourth orthogonal dimension, and then when you bring in to the system momentum and energy, then you rotate that like rest momentum direction towards the total momentum, which is here the Dirac current, because it has this probability interpretation. But this is just like for the for the experts in geometric algebra and space-time algebra, that there could be some really nice commonalities in these, because then you have, then it's not like only like scalar mathematics. It has like a lot of structure of the space available. All right, but then a more like a different approach to the same. So I thought that I could show how I have been thinking how these Suntola diagrams, energy momentum relations, could be related to standard hyperbolic spaces and hyperbolic representations in relativity. And the next slide is horror at first, but let's deal with it. So because there was this question, and I just formulated quickly these relations here. So here we can start really simple, and I didn't have time to really take away all these extra elements. This is how I usually work, that I put these relations also graphically, so then I can confirm my algebra with this graphical thing. So here, let's see if I have it here somewhere. Let's see. Yeah, I can perhaps use this. Yes. So this here is like a fundamental geometry, in a sense that this is just like a hyperbola that could be expressed as an exponential, so e to the w. And in terms of energy momentum relations, then usually the even part, which is the hyperbolic cosine, it is shown as a vertical axis, and then the momentum, which is the odd part, it is shown as the horizontal axis. So then this point here, it is simply the e to the w, which is the hyperbolic cosine plus the hyperbolic sine. And the even and odd part are separated here. So now, usually, you boost or you bring energy to the system, then it stays in this so-called mass shell. So, for example, in high energy physics, you you always, this like encodes the energy momentum relation, like really like fundamentally geometrically. And you can also, using exponential function, you can make different coordinate transformations from the, for example, from Lie algebra perspective, where the U1 is here, so e to 0 is here, and you can rotate to different directions. And now with Suntola, we can one way to understand that geometric relation is by using Ludermannian function or the stereographic projection. It is really simple. You just take this state or this energy momentum state that you are, and then you project to the south pole. And so here is a unit circle, but because this is so symmetric picture, you can always scale it so that this is sometimes called mass gap. So you can scale it so that here it's unit circle, but it could be MC, the radius there. And you project it there, and now this angle here, this angle is marked with x. So it is this x here. Then this hyperbolic angle here, it is this w, and then this stereographic projection to this tree space here. This distance is s, so it is here. So this relation here is really true. It's like a half-angle formula, sometimes called like Weierstrass substitution in some integration. And it's quite amazing that all these relations are true. So let me reiterate. So the hyperbolic angle is the w, then the x is the Euclidean angle here, and then the s is that stereographic projection here. So now we can choose, at least on this kind of a, because this is like a this kind of like a crosscut of this problem. We can choose our representation in a sense that if we like want to represent the energy momentum relations with S, then all the rest are also determined. And it also, it was quite amazing to write these down, because one could see that it's very easy to get into trouble with different representations if you mix these. You can mix them because they are like true, but in mathematics you can just. I have also drawn that diagram. It's an interactive diagram, and you can. I have drawn them with these formulas, so everything lines up correctly. And now the interesting thing here is that normally this element here is the kinetic energy, so it's the extra energy that is gained in this reference frame. And now in Suntola studies, it's this like extra here over the unit circle. And also one can then simply use these formulas to see, for example, when the energy is the gamma factor, or it's multiplied by the gamma factor. Here it's the secant. So in Suntola, in du, it's the secant is the same as the hyperbolic cosine. Also for the momentum, which is the odd part, which is the hyperbolic sine, then here it's just the tangent. And that is, these are quite nice relations that appear in here. And especially it's quite nice that in this diagrammic form, usually the hyperbolic tangent, which is the rapidity, here this is just like a group velocity, and this is like a c in that gravitational time dilate c in that specific setting. We don't need to use that r. Usually this is quite hidden, but here it's simply the sin. So it's this element here. This element here is directly the rapidity. It's exact. Yeah. And also the interesting thing here is, and this is something that some team or some group should really discuss, that is there a reality to these new components here that are now visible? Because usually you just think about the kinetic energy or the extra energy, but here there's this hyperbolic second. So this line here is hyperbolic second. So it's the inverse of the hyperbolic cosine. And Suntola says that represents the remaining like internal energy of the system being accelerated. So there's like a new component here which represents the inertial work. And now for this inertial work we could express it in these hyperbolic coordinates also. It's not only on the Euclidean. So it's an interesting question if there would be that kind of a thing, and what would it happen? Because usually it's not visible and it's not used. Of course, hyperbolic second it appears in all like many in fundamental relations, but would there be something? And because here there's no like basis transforms taken into account, and that might be the thing that really like breaks this in a sense that we have now drawn this just in this kind of a quite static setting, but usually you think that you can boost into other direction. But here Suntola thinks that actually what happens there is that you can boost, both objects can gain the energy from the same environment and their standards lower together. And that is shown as the getting back to the rest frame. And also in terms of what Suntola showed this like an hour or two ago, he had this Doppler effect. So now we can actually see it here, because the hyperbolic sign is the odd component of odd part of this exponential function. Now this e to the w, it's here, and e to the w have all these kinds of wonderful forms here. It was quite amazing to write them down, because I haven't never thought about those. Usually you just think about odd and even. So this here, this is now the representation that shows the cos, which is the element here, so it's the reduced rest energy, and then 1 minus plus sin, which is here 1 minus plus v to c. So it's like a common, it's like a combined reduction of this rest energy combined with Doppler effect. And these are quite amazing symmetries. But also this shows that these are quite difficult to discuss and difficult to go into details, because already this is like too much. But when the thinking progresses, then one can simplify it a lot. And also one perhaps sees that these are like Moebius transformations of the Riemann spheres, because that's what Coulomb interaction does. So. Yes.
Before you move on,
yes.
What if x is larger than 45 degrees?
Here I could show, but actually if x goes to if w goes to infinity, then x goes to pi divided by 2, so it goes to right angle.
Okay, so x can't be higher than.
Yes, yes, but it doesn't go if you hyperbolically.
It doesn't what?
It doesn't go like x stays like compact. Yeah. Yes.
I agree. Yeah.
Yeah.
I mean, it stays less than 90 degrees.
Yeah, yeah. And that's part of why Suntola thinks that you could model these photons going straight through in like vertical direction is these diagrams.
Well, it sounds more like the photons are going diagonally.
Yeah.
It can't go faster than that.
Yes, but here in that Euclidean picture,
This is the Euclidean picture.
there's the Euclidean parabolic and then the hyperbolic
But
pictures.
in Euclidean space, you can rotate as much as you like. You're not limited. It's not like, oh, I'm in Euclidean space and I rotate 90 degrees.
Yes. Yes, by Euclidean I mean, yes, but by Euclidean I mean, but if we exponentially rotate, we get hyperbolic, Euclidean or circular, and parabolic share.
If you're using a hyperbolic transformation, it's more like a hyperbolic space. Right?
Yeah. But these are so fundamental we could discuss this for months. Yes. And then I also made it to 3D, so you can get the boosts into orthogonal directions, and then you get these nice circles here and stuff. So it gets really difficult to go forward. All right, and then the next one, which is the like variable speed of light theories and the variable standards. So here is the table of current physical constants from Review of Particle Physics, only part. And this I promised to open a little bit how it looks like in DU, at this point. And so these are defined as exact, and the main idea in these Suntola studies is to study the idea that if you gravitationally time dilate this C, so you take the gravitationally time dilated C, how would all these other formulas and change, and how would they need to be changed so that things would still be consistent? And we need to first understand the C and the gravitationally time dilated C. And this is from JPL Deep Space Communications and Navigation series. So this is like how actual rocket engineers think about these things. It's really interesting that there seems to be like different communities of practice where this kind of language, where you say that the next approximation amounts for the reduction in the coordinate velocity of light, Vc, below C, due to the gravitational potential of the celestial bodies of the solar system. That it's like bands that you can't discuss because C is like a constant and it doesn't change. But this is often how I've heard that the practitioners in satellite communications, they think about these issues. They just think that, okay, well, light speed varies in coordinate time. And coordinate time is something that is common to all the participants in this gravitational system. If you go far away, then the proper time and coordinate time agree. So in a sense, they think in terms of faraway observers, gravitationally speaking. And they just think, okay, speed of light, coordinate velocity of light is decreasing near mass centers and stuff. And this is not it's surprisingly common to somehow avoid the coordinate speed of light discussions and this this kind of variable speed of light discussions. For example, this is the from the standard definitions, like most definitional definitions that I could find about the definition of the meter. And there it looks like we just calculate with constant speed of light. Also, here the high relative accuracy for long ranges is a lunar ranging. So it gets that kind of a feeling that even in lunar ranging that you use constant speed of light. And that is wrong. So actually in lunar ranging you take the Shapiro delay into account and you calculate in coordinate velocity. Otherwise your predictions don't match the empirical. I can show it quickly. For example, here is from lunar laser ranging the millimeter challenge. It's already 10 years ago, but still like current. You send these pulses. There are many pulses going at the same time. But actually, how you calculate it in barycentric, solar barycentric frame, where the Earth is moving, the Moon is moving. You get these different time intervals here, and then actually here it says that the Shapiro delay associated with propagation through solar and terrestrial gravitational potence must be incorporated, amounting to 25 nanosecond modification to the round trip time. Call it said to one-way equivalent to the Sun, now 0.02 meters from the Earth potential. Propagation through the atmosphere incurs roughly 2 meters path delay that cannot be determined and removed to high precision. So even in this kind of a really like a simple case where many people think that you just send like a constant ping pong to Moon, and still actually you need to account for the curvature of space and the related gravitational time dilation there, which must be the same for the clocks and the speed of light, coordinate speed of light in the vicinity, because that is how proper time is defined for a small spatial place. Also, this same has this by indirect measurement of light traveling time, local interferometer, and there Tuomo has ideas how actually, because the frequency of light is such an important element here. So if the frequency of light changes, then you can invent a scheme where things stay invariant also there. And these are important because in that general relativity book, for example, there were these pedagogical examples. There's observer and laser. Observer drops with the laser. So what actually happens? It's so easy to say that since the observer is at rest relative to laser, he observes his proper wavelength as determined in the skyline. But Suntola says that actually both change in sync. So you don't see it, but you see it when you compare different gravitational states, as for example Shapiro delay demonstrates. But it's a really like a unorthodox thing to start thinking about that the photons don't gain energy by falling, but actually there's a coordinate speed of light that is changing, and that is seen as the frequency increase. But those are like, I think we should have at least that kind of like interpretations available also, and then see what kind of conflicts there will be, because of course there might be different kind of concepts. And now, as Ivette also has demonstrated, the optical clocks are nowadays really accurate. And here is a wonderful proposition by Suntola, is that because these atomic clocks are like these kind of whole systems where you have like resonance chambers and you have electronics, what if it would be like physical, in a sense that you could, from coordinate time perspective, you could look at the clock and look at this physics without using the metric to correct for the thing, but look at the clock. So then there's a like suggestion, or you could say that it's derived from the energy balance in du, where the frequency is simultaneously directly proportional to the rest mass of electrons and then to the speed of light, so gravity in coordinate time. And with those you could model both the electronics and the resonance chambers together, so that actually the Bohr radius would expand at speed, and so the quartz crystals would expand at the Lorentz factor, and that would be exactly in sync with the frequency drop in the clock. And if we wouldn't have like relativity, then this kind of thinking would be really like, I guess, common, like in classical physics, like how on earth the clocks go slower? Because it really seems that many like atomic who actually maintain atomic clocks and think about deal with satellite things, they think that the clock simply goes slower. And gravitational time dilation famously is not reciprocal. So it's common to all observers. And this is quite nice. I didn't believe it first when I see it in Tuomo's books that you could like reproduce the gravitational time dilation curves with this kind of really simple mathematics where you just refer to the common coordinate time and you bring the clock down to the satellite orbit and down to as a reference clock here, and you just take the frequency fractions, and you get the same curves. I haven't plotted them here, but they are plotted on the website, and this gives. But there are so many like conflicting interpretations also in the literature that what this V, for example, is, because some people think that the V is between the satellite and the observer, but these kind of things look like so that the V is in that frame with respect to the larger gravitational mass, and all the object and the observer are both related to that common system. Yes. How much time do I have? So here I can quickly show. This is the last thing here. So the proposition or idea how this could be like consistent, how the gravitational time dilation could work. So if you think about the fine structure constant, which is here, if we insert here the gravitationally time dilated C, then it would not be constant, and that's a problem. So we take the permittivity of free space here, which is 1 over mu C. We put it here. And now the C squared goes up, and this C cancels. Now it's again proportional to C. So now it actually, from like a sort of like first principles arguments, the H must have C in it, so that the fine structure constant is constant with gravitation. And then this permeability of free space here, because it's newtons per ampere squared inverse. Newton is inversely proportional to second squared, and then ampere is coulombs per second. So they cancel, the seconds cancel. So the permeability of free space is sort of, at least here definitionally, not dependent on the gravitational time dilation. So then the classical electron radius and the Compton wavelength you can also, similar reasoning, now use that intrinsic Planck constant to see how they react to gravitational time dilation. And the C is here, both of these classical electron radius and Compton wavelength and Bohr radius. All the C's are cancelled away. So it's not proportional. Objects stay the same in different gravitational settings. But there will be this M. So it's like proportional still to the rest mass, which is variable. Yeah. Yes.
Thank you very much. Do we have any quick questions here? We can move while the next speaker will be setting up. There's Callum.
Okay, so go back to the slide where you said that you have the element in the elementary textbooks. You have these examples that don't take changing speed of light into account. So in general relativity, you do get this effect where the speed of light changes relatively according to the.
Yes.
So the example you've given, I think, unless I'm missing something, because it's using the Schwarzschild method, it should already take into account any change in speed of light. The point is you're just using C in, the point from GR is that C is the same for all observers in their reference frame.
Yes.
But in fact, what C is doing is it's just telling you that geometrically you have a division of your space-time into the time-life, space-life, and light-life parts. So in a sense, the value of C doesn't matter. What matters is the relative tipping or expansion and contraction of the light cones as you move through the space-time. So in that sense, it's correct that GR already includes a change of speed of light, but it's incorrect to say that, for example, this problem would change if you included the variable speed of light, because any variation in the speed of light is taken into account through the Ernst's or the Einstein theory.
And I'm not saying that the physics here would say, but the interpretation, especially for philosophers.
But physics is important, but you can't just say this has no change in speed of light when it does. I mean, that's not science.
So, are we ready to move on? So let's thank Petri.